All right, welcome back. Hononegah Honors, Algebra 2, Section 6.1. We're starting off with a new chapter, and everything in this chapter is basically dealing with exponents. A lot of exponent type stuff, and so the first one here we're talking about is what's known as exponential growth and decay. An exponential function has the form of y equals ab raised to the x, where a is can't be 0, and the base b must be a positive number. Can't be 1 because, again, 1 to the second, 1 to the third, 1 to the fourth would be a flat line. So b can't be 1. Now, the picture below, so if you have an a value that's greater than 0 and a b value that's greater than 1, so we got an a value greater than 1 or greater than 0, sorry, and a b value greater than 1, then y equals a b to the x would be considered an exponential growth equation. So the a value is greater than 0, so you're talking about positives, and the b value is greater than 1. So this would be the example of the picture for an exponential growth function. So notice from left to right, it starts off really small and then obviously grows exponentially. Now, the first time we've ever talked about what's known as an asymptote. An asymptote, in this case, is the x-axis, and the asymptote is a line that the graph approaches but does not cross. And we're going to be dealing a lot with asymptotes as we go through some of the other chapters in the book. And so an asymptote in this case is the x-axis. And so you'll notice as the graph goes to the left, it comes really, really close, but never actually crosses or touches the x-axis. So again, just keeps getting infinitesimally smaller, but not actually touching. So the domain is going to be all real numbers, and the range would be y is greater than or equal to, or greater than, sorry, 0, because it doesn't actually touch 0. Now, what happens if your b value is, we still got an a value greater than 0, but the b value now is less than 1, but still positive. So you're talking about all fractions or decimals. So a b value of a half or a third or 0.5. Those would all be examples of exponential decay factors. So notice the graph as it goes from left to right, it goes downward. And again, you still have the x-axis as an asymptote. And so it approaches the x-axis but doesn't actually touch the x-axis. So this would be, again, all real numbers. And y would be greater than 0 again is your range. Now I can change my a value, and we'll show that in some different pictures here, but the b value will always be between those two values. So here we go. Graph. Pull out a graphing calculator if you want, and I'm going to pull one up here in just a second, but 1.3 raised to the x power. So I'm going to make an xy chart, and basically I'm going to plug in some numbers for x. So 1.3 to the 0 power would be 1, 1.3, this is 1.69. So I know some of those off the top of my head, but I'm going to pull up a graphing calculator. We're going to look at these numbers. So 1.3 raised to the x power. So y equals 1.3 raised to the x power. So graph. So notice exponential growth. And so I want to get some points here. So I'm going to hit second in graph. And my table set is going by 0.25 from last chapter. So I'm going to change this to going by increments of 1 just so I can see more points here. So there's my graph again, my table. So notice 0, 1, 1, 1.3, 2, 1.69. If you want to go all the way up to like 8, 8.175. So again, just to get a better picture. So I'm going to write some of those down. 8, 8.75, I think was on the, 8.15. Sorry, I didn't write that down right. 8.15. Let's look at some negative numbers now. Let's go back to the calculator, and let's arrow up. So I got, notice the numbers keep getting smaller and smaller and smaller and smaller, but they never actually get to 0. So let's graph as many of these. Negative 1.76, negative 2.6, 0.76, 0.6. So again, graph as best you can, obviously. So it's going to keep getting smaller and smaller, and then you're going to get to 1, 1.3, 1.69. And notice that I went all the way up here to 8 just so I could get a better picture of the exponential curve. And again, it's going to ask you if it's growth or decay. Because this number is above 1, that's exponential growth. So looking at the next one, I can do that right away. That is decay. I know that's decay because the B value is between 0 and 1. Now, XY chart. -2 is 9. -1 is 3. I can do this one in my head, but obviously you can use a graphing calculator. So I've got -2, +9, -1, +3, 0, 1, then a third, a ninth, and so again, it's going to keep getting smaller and smaller and smaller, but it's never actually going to touch the x-axis because that's an asymptote. All right, next one. A couple of models that we're going to use, and I'm going to give you these formulas when we go to the test, like an exponential growth model, exponential decay model, but you're going to still need to know what each stands for. So the A value in the model is the beginning amount or initial amount. And it's right down here. A is the initial amount. R is the percent of increase. Now, when you put it into, or decrease in this case, so it's always R, it's plus the rate or minus the rate. So if you get a 4% increase, you're going to put 0.04. So when you put it into the formula, you're going to write it as a decimal. And then T is the time, and it's time now growth factor and decay factor. When you actually do 1 plus R, that is considered the growth factor, and when you do 1 minus R, then that is considered the decay factor. So it's R is the rate, and then 1 minus R would be the decay factor, 1 plus R would be the growth factor. So here we go. The value of y in thousands can be approximated by the model y equals 31.92 t, where t is the number of years since the car was new. Tell whether the model represents growth or decay. Because the b value, or in this case below 1, this is a decay, so exponential decay. Identify the annual percent rate of the increase or decrease. So remember, the formula was a 1 minus rt. Well, if this is equal to 0.92, then what does r actually equal? If I subtract 1, divide by -1, r would equal 0.08, or 8%. It's the actual percentage of the decrease. Now, estimate when the value is 9,600. So 9,600 is when, and I have, now it's in thousands, sorry. So this is 9.6, 31.92 raised to the t power. And we are estimating here. As far as later on, we are going to actually solve things like this. So let's pull out a graphing calculator. I apologize. We're going to erase this. And I want to type in y equals 31.92t into my graphing calculator. And I want to estimate when it's going to be in 9,600. So let's pull out a graphing calculator. Let's type that in. So y equals 31.92. We're going to raise that to the t power, or x. Later in the chapter, we're going to be way more precise on this, but right now we are just going to hit second, graph, and we are looking for when it is going to be close to 96. And go back to 9.6. So where is it at 9.6, or at least close? So it looks like we're at 14 years. Okay, so right about almost 14 years is when it's going to be, so a little less than 14 years. So go back over here, estimate when the value of the car will be 9,600, almost 14 years. And again, we're going to get way more precise as this chapter goes along, but right now we're just estimating when it's going to be that way. Next one, in 2000, the population of the city was 1.04 million. During the next 14 years, the population increased by 2.05% each year. write the exponential model. So we're talking about an increase. So y equals a 1 plus r raised to the t. So it's saying that we started off with 1.04 million. We're at a rate of 2%, 2.05% raised to the t. This would be the model. And so the growth factor in this case would be 1.0205. So if they ever asked you for the growth factor, that's what they're referring to. Now, estimate when the population will be 1.3. So we're going to type this in again, and we're looking for a y value of 1.3. So pull out the calculator. Y equals 1. Whoops, we got to clear that. 1.04. And I believe it was 1.0205 raised to the x. And so I'm looking for, what was it, 1.3? So when would it be about 1.3? You're talking about 11 years. So we're going to go back over here, and we're looking for when would it be 1.3? About 11 years. So if you had a t value of 11, then you're going to notice when that's 1.3. The amount y, they're going to give you an equation here. So the radioactive isotope barium-140 remaining in a t days is y is equal to a, parentheses 0.5 raised to t over 13, where a is the initial amount. What percent decays each day? So they want to know what the r is. So again, a 1 minus r raised to the t power. And I know it's t13. So that really messes with how this is worked. So this is a 0.5 raised to the 1/28th. Oh, sorry, the a value is outside of that. T. And so then what is 0.5 to the 1/28th power? So pulling out a calculator, I want to find what 0.5 raised to the, so 0.5 raised to the 1/28th, and I'm getting 0.9755. We're going to round to 4 decimal places there. So 0.9755 t. So that changes everything. So notice that here is the number that's being raised to the t power. It's not 0.5. It's actually 0.9755. So that changes things up a little bit here when I start talking about 1 minus r equals 0.9755. So if I subtract 1, negative 0.025, and so r is equal to 0.0245 or 2.45%. So what percent of barium is each day? So this is actually every 13 days it goes down by a 0.5, but they want to know what each day would be. And so I apologize. I just looked at that, and so I have to go back and erase this. This isn't 1/28th. It should be 1/13th. I'm not sure why I saw 28 up there, but it is not 28. It's 1/13th. So let's start this thing over again. A 0.5 raised to the 1/13th. So again, I apologize if you were watching this video. So I have to go back here. 0.5 raised to the 1/13th would be 0.9481. And so now going back to what I just did before, 1 minus r is 0.9481, which gets me negative 0.0519. So you're talking about 5.19%. So I apologize there. I don't know why I saw a 28 there, but it's really a 13. So again, hopefully you guys were able to stop that, go back and question that. And again, I didn't want to start the video completely over. Next formula, I'm just giving you another formula. This is actually referred to as compounded interest. So the p-value is, again, the initial amount. It's what's called the principal amount. A would be the ending, so just like before. R, now this is a little different. R is still the rate. N is the number of times per year the interest is compounded. And so this is N times T. So again, the number of times that it is compounded by the time. So if you compound it 4 times a year or quarterly, and you do it for 4 years. So 4 times a year for 4 years, that would be 16 then. Would be there. So here we go. Let's do a problem using that formula, and I will give you that formula. So the A equals P, 1 plus R over N raised to the NT. You don't have to memorize that formula, but you obviously need to know what each thing means. You deposit $8,600 in the bank at a rate of 1.32%. So remember to write that as a decimal, not as a percent. Find the balance after 4 years if the interest is compounded quarterly. Quarterly means 4 times a year. So 4 times a year and 4 years. So that's what you want to be able to type into your calculator. And it does require a little bit of parentheses, and you got to be careful. So I always figure out what's inside the parentheses first, and then raise that to the correct power. So using my calculator, I want to try to figure out what 0.0132 divided by 4 is. So what is 1 plus 0.0132 divided by 4 is 1.0033. Yeah, I typed it incorrectly. So 1.0033. So now my calculator, 8,600, 1.0033 raised to the 16th. So 8,600 1.0033 raised to the 16th power, and enter. And so $9,065.49. So $9,065.49. Your homework assignment is out of the book. I apologize for that one example. Hopefully you were able to figure that out. If you have any questions, please make sure you talk to your teacher. Starting with chapter 6, new chapter, kind of getting close to the holidays. So everybody be safe and take care.